All right, let's look at an example of our first force that we are going to talk about, and that is gravity. I'm pretty sure you have some kind of inkling on what gravity is, but there is still a lot of misconceptions out there about gravity, all the way to the point that at some point scientists even today disagree that this is even a force. But our book does mention it as a force, so let's talk about it in that capacity, and we'll discuss a little later on why it might not be. Gravity is what's going to be called a force that pulls objects towards each other. So any two objects you have, there is an attraction force between them called gravity. The more mass you have means the more gravity you have. So why do you not attract to other things? Well, that's because you all attract to the Earth, which has more gravity and mass than anything else you probably are near. Um, the sun has a lot of mass too, and that's why the Earth is getting pulled and caught in the orbit of the sun. We're just falling, so we keep missing the sun as we fall towards it and make it a orbit. So any two objects are going to exert a force of gravity. The more mass you have, the more gravity you tend to exert. Our law of universal gravitation states that gravity acts everywhere in this universe. You cannot escape it. You're always going to be pulled towards something that has a larger mass than you. So any two objects will attract each other. Other gravitational forces are small compared to the Earth, and that's why you really get more attracted to the Earth as opposed to the chair that's sitting next to you. You don't kind of move towards that. That attraction is just very weak, and Earth's gravity is pulling harder. Uh, so the Earth's gravitational force will win out. There are two factors that are going to affect gravity, and that is going to be mass and distance. The more mass you have, the more gravitational pull you have. Again, the Earth has a lot more mass than you, and therefore the Earth tends to pull out compared to you dragging the chair next to you towards you. And also distance. The more distance you have, the less gravity. So the further two things are away from each other, the less the gravity affects on them. And this is why other galaxies, you might not actually feel the actual force of gravity on you right now. However, those galaxies do exert a force on our galaxy and causes them to move around and things like that. The sun. Yep, the sun is very large, and therefore it keeps the planets in orbit. The sun is all exerting that force of gravity on all of our planets, trying to attract them to it. However, we do have a constant velocity going around them, so we keep, as we go think about falling, we're not technically falling towards the sun, but as we fall towards it, we move, we just miss it basically, and instead of falling towards it, we fall around it. And that's what an orbit is. All the planets are in their orbit. They are in ellipses, not circles. From Johannes Kepler told us that. But you can think that the orbit of Mercury is much smaller than the orbit of Pluto because of distance. Um, the sun's gravitational force is a lot stronger on Mercury than it is on Pluto, just because Mercury is closer than Pluto. But we are falling around the Earth, the sun, not necessarily towards it. Which brings us to our idea of free fall. I'll move my head out of the way so you can see that accurate. I'll put it over here. The idea of free fall. Free fall is when the only force acting on an object is gravity. Then it's said to be in free fall. So just like we get that weightlessness sensation on like amusement park rides when you're going down like a hill on a roller coaster, you feel that weightlessness sensation. That weightlessness sensation is just eliminating all forces acting on you but gravity and putting you in a free fall. This is also why astronauts float around as they orbit the Earth. It's not because of the lack of gravity, it's actually because gravity is the only thing acting on them, and they are therefore falling towards the Earth. But again, they are in orbit, so they're actually falling around the Earth. They just keep missing the Earth as they go past it. What is also important is that gravity is going to accelerate objects at a constant. It is a 9.8 meters per second squared acceleration. That number needs to be memorized. Write it down a few times in your notes. 9.8 meters per second squared is the acceleration of gravity. If you decide to drop an object off a building, it will accelerate at 9.8 meters per second squared. I don't care what that object is. They all will accelerate at 9.8 meters per second squared. That is until they reach what's called a terminal velocity, and therefore they will no longer accelerate, and certain objects will reach that before others. Which brings us to air resistance. Normally when you drop something, gravity would be the only thing acting on it, but we do have air resistance because air is matter. There are particles in that air, and as you fall, you are smacking into these particles. As you smack into those particles, Newton's third law says those particles are going to exert a force on you that is equal in magnitude and opposite in direction, so they will be pushing up on you. This is what we call air resistance. So think about you free falling through like water or something. That would be water resistance. You can't just fall right down to the bottom very quickly because all of those water particles are pushing up on you. However, in air we have a lot less of those particles, so you fall through it fairly easily, but they are still there pushing up and decreasing your momentum or your velocity. Once they do decrease it so it is equal to the acceleration of gravity, then you will be exhibiting your terminal velocity, and therefore you will not be accelerating anymore. So this is your parachuter. This is a great essay question I tend to ask, but if you can explain how the parachute works. Well, when I jump out of my plane, I have my parachute on my back all folded up nicely, and I have whatever's on my body, and the mass is not going to change as I fall. Therefore, the acceleration and force of gravity is a constant, being 9.8 meters per second squared. It's not going to change at all either. The only difference is that when I decide to deploy my suit, I am increasing my surface area, and this suit is like catching all those air particles as it goes in there and increasing the amount of times I slam into those air particles, therefore increasing the force they're applying up on me. So as I fall, the force of gravity is going to stay the same. It's going to be a constant. There is no change there. However, the force of air resistance I can increase by giving a greater surface area. This would also be why a feather can fall slower compared to a tennis ball. That feather has a larger surface area to catch more of those air particles, and therefore has a larger air resistance, and it will reach its terminal velocity and slow down that acceleration due to gravity. However, the force of gravity is a constant. It does not change, which is extremely important to understand.